Okay, I want to talk about diagonalizable matrices, trace and determinant, because they have some nice relationship. So let's say A is diagonalizable, meaning that there's a matrix P where P inverse AP is a diagonal matrix. Or you can also multiply P both sides on the left and then P inverse both sides on the right, and write it as A equals to P inverse, no, P times D times P inverse. And then here, D is like a diagonal matrix. There's 0 here, 0 here, and only non-zero values are on the diagonal. Now, if that's true, then you can read off this multiplication, AP equals to diagonal times, no, AP equals to P times diagonal. If you multiply P both sides on the left side, P and P inverse will cancel and you get this, right? AP equals to PD. And if you look at the column vectors of P, name them as V1 through Vn. And if you call this lambda 1, lambda 2, lambda n, oh no, D is next. So V1 times V2, Vn, and then lambda 1 times lambda 2, lambda n. Then, again, using the same logic that I talked about before, this times this entire matrix only multiplies lambda 1 on the first one, right? So if you do this calculation, you see that lambda 1 V1 is what you get on the first column, lambda 2 V2 is what you get on the second column, lambda and Vn is what you get on the last column, and matching these, you see that each individual columns of the P are eigenvectors of A with eigenvalues lambda 1 through lambda n. So in other words, this diagonal, the diagonal entries are the eigenvalues. Okay? Along with these, there are some other nice properties of a diagonal matrix. So if you have a diagonal matrix, it's easy to calculate the trace and the determinant. So first, let's talk about the trace. What is the trace? It's the sum of the diagonal entries, right? That's what the trace is. So ignore everything else. You just add the diagonal entries, and that becomes lambda 1 plus lambda 2 plus lambda n. So a diagonal matrix has the trace as the sum of all the eigenvalues. And determinant of a diagonal matrix, if you try it, then it's, if you do a row expansion, it's lambda 1 times the determinant of this small one, but then it's 0, 0, 0, everything else. And you repeat the row expansion here and here and here, and eventually you see that the determinant will just simply be lambda 1 times lambda 2 times lambda n. That's what you get. Now, surprisingly, the traces and determinants have some nice properties. So first of all, trace of A times B, you can show that this takes some time to actually do the proof, but if you actually write all the elements down of A times B and then trace, you see that same thing as trace of B times A. And this means that if you have the trace of P times D times P inverse, you can think of this one as A and this as B. Switch its place using this property that we just did. Trace of P inverse P times D. And these two will cancel. So it's going to be trace of D, which is the sum of all the eigenvalues. But wait, what is this? This is our A, right? So the trace of A is same as sum of all the eigenvalues. So this is a nice fact. Trace of A is equal to sum of its eigenvalues. Now, this is for diagonalizable matrices, but even if it's not diagonalizable, if you make the Jordan canonical form, you can see that trace is indeed sum of all the eigenvalues with multiplicities counted. Okay? And then same thing can be done for the determinant. For the determinant, it's even stronger. This is same as determinant of P times determinant of D times determinant of P inverse, and then inverse can even be pulled out. So that, because this is a number, it's 1 over this number, so they cancel. And you end up with determinant of P, determinant of D, which is lambda 1 times lambda 2 times lambda n. And because this thing here is A, we see another fact that determinant of A is the product of its eigenvalues. Again, this would be true for matrices that are not diagonalizable. If you just have its Jordan canonical form, again, the diagonal entries multiplied will be your eigenvalue. It will be your determinant. Okay. Yeah. So sometimes you wonder, what's a determinant? Well, determinant can have many different meanings. I explained the geometrical meaning of it, but one meaning is it's the product of all of its eigenvalues. Just one final remark. This thing here, I'm a bit embarrassed to say that I learned the true meaning of this only in my 3rd year of grad school. So I knew this was true, but then I thought this was always true. But see here, here's the important part. Trace of ABC is not equal to trace of BAC in general. It's not like you can commute everything. So this one is called a cyclic property of trace. And what it means is that you can only take something at the end and put it in the first. You can only do that. Yeah. So what's true is that trace of ABC is equal to trace of CAB. But if you just internally switch two things, it's not true. You can easily find examples where this is not true. So don't ever confuse that property, but that's true in general. Okay, thank you.